so then from yesterday, to elaborate, to be more clear, again, time intervals, when you're looking at time intervals, you're finding the average velocity over that time interval. So by doing that, the reason you're doing that is because it is just the change in the function, okay, change in s over change in time. Okay, that's just, all you're doing is rate of change, and you're doing the average of that over time. That's why we're dividing it by time. Okay, then what we talked about, we went further. So this is a really good example of, so a secant line, if we find the average velocity, it's not a tangent velocity, okay, or not a tangent line, because we already talked about yesterday how I was going through the parabola, and Morgan was asking how does it go through the parabola and how does it not. This is an average velocity, so it just goes through it because at that point it's the average. Okay, now the average, is it, like that's what we're saying is that what it for sure is at that time? No, it's an average. It's what it could be. That's why the slope just kind of stays the same here. But if we do the instantaneous velocity, that's going to be tangent because it's a specific, okay, it's a specific velocity at a specific time. So it's instantaneous, so it hits it at one spot. Okay, the average could hit multiple spots because there's different time frames that could have that average. A secant line is the one that goes through. Yeah, secant goes through two spots because that's the only way it could, right? If it's a straight line, it could go through at 2 spots. Yeah. Okay. Any other questions? So secant line goes through 2 spots. Tangent hits at 1 spot. Okay, and I forgot what the one that doesn't hit at all is called, but we'll get to that some other time. Okay, all right, so that's kind of to show you that illustration there. So again, instantaneous hits that 1 point being tangent. All right, let's kind of skim through here. What else did I want to review before we do our last example? Okay, so then instantaneous, we use limits to find instantaneous velocity because it's approaching one speed, or one set of velocity. That's not right. It's approaching a velocity. There we go. Okay, and so we use our limits for that, and that's what we did in 1.4, so we're familiar with that same setup. And there's our temperature one. We talked about that again. I already want to talk about that. All right, so that's good. Okay, so for example 4, what we're going to do is, this one's going to be a little bit challenging in terms of it's not super easy, but a spherical balloon is being inflated. Find the rate of change of the volume with respect to the radius when the radius is 10 centimeters. Okay, so it gives me 10 centimeters. Okay, so that is going to be what we're going to use as our instantaneous velocity, okay, or volume for this one. Okay, now that's why this section is called velocities and other rates of change. This is still a rate of change. What is being changed here? What's happening with this? Think about this big picture. Spherical balloon is being inflated. So if it's being inflated, the spherical balloon is what? Expanding. Exactly. It's getting bigger. Okay. Find the rate of change of the volume with respect to the radius when the radius is 10 centimeters. What it's saying is, when you have the balloon up to 10 centimeters, how much faster, or like how much more, how fast is the volume changing at that point? That's what you're looking for. So will we be expecting a positive or negative growth? Is it getting bigger or getting smaller? It's getting bigger, so we should expect a positive volume growth there, okay, for rate of change. The other thing I would say is, if we're thinking, when you're filling up a balloon, right, and you're putting air into it, does the amount of air it takes slow down, or does it keep contracting? Like, do you see what I'm saying? Like, as it gets more and more full, yeah, it kind of slow down, right? Because what's happening is it's going to start pushing back because it'll overexpand and pop. Okay, so there is breaking points to my point. Okay, we won't really see that. I just want you to think about those kind of things when we're talking about realistic problems. Okay, so this one here. Okay, so what we know is, we know the radius. We're looking at when the radius is 10. Okay, and so what we're going to be doing with respect to, we're going to be looking at the limit. Okay, it's a change in r, so the change in the radius. That's what we're looking at, the change in the size of the balloon. Okay, goes to 0. Which is change in V, which is change in volume, over change in R, which is the change in the radius. Okay, we're using change in R because that's what we have. Just like time, we had time, right? Okay, so what that would equate to in terms of how we're going to solve, it's going to be limit. I did R goes to 10, so I use this instead of the H one. Remember, we can do either or. Okay, as R goes to 10, we want to look at V of r minus V of 10. That's our function. And then over r minus 10. So radius minus the radius we were given. Now, where am I getting V from? How can I conclude where I want to get V from? What is V? What's that? No, it's not my x. R is actually our x. The radius is our variable here. But what I'm saying is, V, we understand that V stands for volume, right? Because V up here in the problem, it says volume. Okay, so the next thing your mind needs to go to, what am I finding the volume of? A sphere. So we need the volume of a sphere formula. Okay, so that's 4/3 pi r cubed was the volume of a sphere. That's what V of x is, or in this case, V of r. Yeah, I'm sure you got to remember that, right? It's off the top of your head. Okay, so V equals 4/3 pi r cubed. So that's what I'm going to put for my V of r. So when I do V of 10, where's 10 going? For r, exactly. 10's going for r. Okay, I'm not going to write what 10 cubed is yet, and I'll show you why. So we're going to keep working through this here. So now I have limit as r goes to 10 of V of r, which is right here, okay, the volume. So 4/3 pi r cubed minus 4/3 pi 10 cubed. Okay, all over r minus 10 still. And see, this is still the hang-up, right? We can always plug in a limit right away if we can, but if I put 10 in here, what's my problem? I have a 0. So we're not done yet. Okay, so this is where we got kind of think outside the box, and this is where calculus can probably frustrate you, because you will get this formula, but we need to get this somehow simplified up here. So that's what I want you to always think of, like, how can I simplify this? Okay, what's that? Yeah, you could pull 4/3 and a pi out. That would help. Okay, so let's do that first. What did you say, Emily? Did you say this? Yeah, you could do that as well, but I'm just going to pull that. In my notes, I just took out the 4/3, but that's fine. So 4/3 pi is going to come out. That's the only thing I take out. I can't take an r cubed out, right? And so that leaves me on top now is an r cubed minus 10 cubed. Anybody see it now, what we can do? So it's fairly new to this unit. Difference of cubes. Yeah, Kate's got it. We want the difference of cubes. These are 2 cubes that have a difference. Okay, that formula is on the Google Classroom. Okay, I put it up there so you can see that if you ever need to refer to it. It is in the book as well, on like the very first section. Okay, so the difference of cube breaks this down, and why this helps us is because it's going to get rid of this for us. So I'm going to go 4/3 pi, okay, and then it's going to break down to r minus 10, and then it's r squared plus 10r plus 100. That's another way of factoring the difference of cubes there. All over the r minus 10, which we're happy now because these cancel, and now I can actually take the limit. So I'm going to have limit as r approaches 10. Okay, of 4/3 pi r squared plus 10r plus 100. Okay, at this point, we are ready to compute. Okay, we're ready to put this in our calculator or just calculate this, and that would be, so this would be 100 plus 100 plus 100. That's interesting. Okay, so we get 300. It'd be 1,200 over 3. It ends up being roughly, with the decimal, 1260 would be your answer there. So what that means is 1260, we are talking about centimeters. So it would be 1260 centimeters yeah, 1260 centimeters cubed. That's right, yeah. Spherical balloon is being inflated. Find the rate of change of the volume with respect to the radius when the radius is 10 centimeters. Okay. let me really quickly, actually want to check. Let me check what those units are. So it's actually centimeters cubed, like you said, but per centimeter. So what that means is, as it's expanding, the radius is expanding a centimeter, the growth is 1260 centimeters cubed for the volume. So it's the relationship between the volume growing and the radius growing. So as your balloon gets bigger, your volume gets bigger. Okay, so 1260 centimeters cubed, so that's the three-dimensional area. It gets that much bigger at this instantaneous, not velocity, it's an instantaneous rate of change for every centimeter of growth in the radius. No, because the radius is still a line, so it's just a single flat line. Okay, I see what you're saying in terms of simplifying it, but you won't write it because you want it in terms of the units of, because this is how it's growing in terms of the volume and compared to the length. Okay, all right, and that's it for lesson 5, or excuse me, example 4. Lesson 5. I was right. Okay.